Hi friends, this is Naresh. In this session, I am going to explain about bars of varying cross sections problems. Uh, in previous class, already we have discussed about bars of varying cross sections with the uniform loads. But in this session, I am going to explain about some simple problems on bars of varying cross sections with variable loads. Okay. Yeah, this is the example problem. Here, this type of problems we will discuss in this session. Before going to the problems, first of all, you have to know the formulas for bars of varying cross sections. This is a example problem. This bar consists of three different diameters: D1, D2, D3 are the three different diameters. So I consider these three as three sections. Okay, A1 is the area of the first bar. Okay, so pi by 4 D1 square is the area of a first section, and D2 is the diameter of a second section. So A2 is the corresponding area. So area 2 equal to pi by 4 D2 square. Okay. Now D3 is the diameter of the third section, where that the corresponding area is A3. So therefore A3 equal to pi by 4 D3 square. Okay. Here P1, P2, P3 are the three different loads acting on the bar. Okay. And L1, L2, L3 are the original lengths. L1 is the original length of the bar 1. L2 is the original length of the bar 2. L3 is the original length of the bar 3. As well as delta L1, delta L1, delta L2, delta L3 are the deformation changes, deformed length. Okay. Already in previous class we have discussed about stress, strain, change in length, Young's modulus. Okay, so already we know the formula for stress. The ratio of load to the cross-sectional area of the section is called stress. So the formula for stress equal to load by cross-sectional area. So the units for stress is Newton per mm square or Newton per meter square. Okay, so this is the formula. Sigma is the symbol of stress. Okay, stress is indicated by symbol sigma, and load here P is the load and cross section area is A. Okay, A is cross section area, P is the load. Here the stress induced in the bar 1. Okay, the stress induced in the bar 1 is equal to sigma 1. I consider sigma 1 for stress induced in the bar 1. So the formula for stress equal to load by area. So here the load acting on the bar 1 is P1. Okay, so P1 is the load acting on the bar 1 divided by cross sectional area of the bar 1. So A1 is the cross section area. So this is the formula for first bar. Similarly, for a second bar, stress induced in the bar 2 is equal to sigma 2 equal to load acting on the bar 2 divided by cross sectional area of the bar 2. So sigma 2 equal to P2 by A2. P2 is the area, so P2 is the load acting on the bar 2, and A2 is the cross sectional area of the bar 2. Okay. And similarly, the stress induced in the bar 3 equal to sigma 3 equal to P3 by A3. So P3 is the load acting on the bar 3, and A3 is the cross sectional area of the bar 3. Okay, so these three are the stresses induced in each bar. Okay, now L1, L2, L3 are the original lengths. Okay, already we know the formula for strain equal to stress. Already we know the formula for Young's modulus. From Young's modulus formula, Young's modulus equal to stress by strain. Okay, from that formula I consider strain equal to stress by Young's modulus. Capital E is the Young's modulus, sigma is the stress, this one is the epsilon is the symbol of strain. Okay, strain is indicated by symbol epsilon. There is no units for strain. Okay, no units for strain. Okay, because the stress and Young's modulus both are in same dimension, so there is no units for strain. Okay, here sigma 1 is the stress induced in the bar 1, and E1 is the Young's modulus for material, for bar material. Okay, so already we know the formula for sigma 1 equal to P1 A1, P1 by A1. So the formula for strain induced in the bar 1 equal to epsilon 1 equal to P1 by A1 E1. So this is the formula for strain induced in the bar 1. Similarly, strain induced in the bar 2 equal to epsilon 2 equal to stress induced in the bar 2 divided by Young's modulus. Okay, P here sigma 2 equal to P2 by A2. So P2 by A2 into E2 is the formula for strain produced in the bar 2. Okay, similarly, the formula for strain produced in the bar 3 is equal to epsilon 3 equal to sigma 3 by E3. So sigma 3 equal to P3 by A3. So the formula for strain in bar 3 equal to P3 by A3 into E3. So these three are the formulas for strain induced in each bar, and these three formulas are for stresses induced in the each bar. Okay, by using these formulas, stresses and strain formulas, you have to find out the value of change in length or deformed length. Okay, when you are applying a load on the bar, then there will be a change in the length. It may compress or it may elongate. Okay, depends upon the type of load. If you are acting a tensile load, then the bar will extend. Okay, similarly, if you are acting a compressive load on the bar, then the bar may compress. Okay, so first of all, you have to know the formula for change in length. Change in length is equal to strain into L. Here already we know the formula for strain equal to epsilon equal to change in length by original length. Okay, so uh, here delta L is the deformed length. Okay, capital L is the original length. Okay, so this one E is the symbol of strain, that is epsilon. Okay, delta L1, delta L2, delta L3. These three are the change in length in each bar. So delta L1 is the change in length in bar 1, delta L2 is the change in length in bar 2, delta L3 is the change in length in bar 3. Okay, so here already we know the formula change in length equal to epsilon into L, that is strain into original length. So here L1, L2, L3, these three are the original lengths. So for section 1, for bar 1, you have to consider L1 as original length, delta L1 as a change in length. Okay, substitute the value of epsilon, that is here this is the value of strain, that is P1 A1 E1. So P1 E1 A1 is the value of strain and L1 is the original length. So this is the formula for change in length in bar 1. Okay, this is the formula for change in length in bar 2. Okay, this is the formula for change in length in bar 3. Okay, here the formula for strain is equal to P1 by A1 into E1. Okay, from this formula you have to find out the value of change in length. So the change in length equal to strain into L. L is the original length. Okay, L1, L2, L3 are the original lengths. Okay, so by using these three formulas, you have to find out the total deformation in the bar. We have to find out the total deformation or change in length. Total change in length or total deformation in the bar is equal to delta L. Okay, delta L is the total change in length or total deformation in the bar is equal to sum of these three deformations. Okay, delta L equal to delta L1 plus delta L2 plus delta L3 is the formula for total change in length. So delta L equal to delta L1 plus delta L2 plus delta L3 equal to P1 L1 by E1 A1 plus P2 L2 by E2 E2. E2 A2 plus P3 L3 by E3 A3. Okay, this is the formula for total deformation. Total deformation or total change in length. In case of tensile loads, we consider as a total increase in length. Okay, for example, in case of compressive loads, you may consider this formula as a decrease in length, total decrease in length. Okay, so here there is a one important condition is there, that is positive sign and negative sign. Here the positive sign means tensile load, okay, and negative sign means compressive load. Okay, when you are applying a tensile loads, then there is an increase in length, so therefore you have to consider positive sign for tensile loads. Okay, if you are applying a compressive loads, then the then there is a decrease in length in the bar, so you have to consider negative sign for compressive loads. Okay, it is very important in our problem. Now I am going to explain about one basic point, that is the principle of superposition. Okay, when a number of loads are acting on a body, the resulting strain according to principle of superposition will be the algebraic sum of the strains caused by individual loads. Okay, already. So this is the form. This is the example for a principle of superposition. Okay, already we have discussed about formulas used in this type of problems. So the formulas for a principle of superposition are same as previous formulas. Okay, while using this principle for an elastic body which is subject to a number of distinct forces, tensile or compressive, at different sections along the length of the body. First, the free body diagram of individual sections is drawn. Then the deformation of each section is obtained. The total deformation of the body will be then equal to the algebraic sum of the deformations of the individual sections. Okay. So, here already we discussed about formulas. Okay, for determining the total deformation in the body, we have to add all deformation, individual deformations. Okay, so that is the delta L equal to change in length, delta L equal to delta L1 plus delta L2 plus delta L3 plus and so on. Okay, delta L1, delta L2, delta L3, these are the individual deformations. Okay, delta L is the total deformation. So for getting a total deformation in the body, then you have to add all individual deformations. Okay, that is the principle of superposition. Now I am going to explain with problems. Yeah, the problem is a steel bar 25 mm diameter is acted upon by forces as shown in figure. Find the total elongation in the bar. Take Young's modulus, capital E equal to Young's modulus, E equal to 200 GPa, 200 gigapascal. Okay, this is the problem. Here the diagram is given. Okay, so this is a given diagram. Okay, here you can observe here this is a uniform cross section. Okay, that means the diameter is same. Okay, the diameter is uniform. So here the cross sectional area for this bar and this bar and this bar, okay, all are same. Okay, here a steel bar 25 mm diameter, so the diameter of the bar is equal to 25 mm. Okay, here three sections are given, that is AB section, BC section and CD section. That means you have to consider AB as bar 1, BC as bar 2, CD as bar 3. Okay, so these are the original lengths. L1 is the length of the bar 1 or length of the section AB. Okay, L1 equal 500 mm and L2 is the original length of the bar BC. So 700 mm is the original length of the bar 2 and L3 is the original length of the bar 3. that is 800 mm for length of the section CD. Okay, so by using these details, you have to find out the total deformation in the bar. Total elongation or total deformation or total change in length is same. Okay, so by using these details, you have to find out the total deformation or total elongation in the bar. Okay, here capital E means Young's modulus. Young's modulus equal to 200 gigapascal. So 200 gigapascal is the example for steel materials. So you have to find, first of all, you have to convert this GPa into megapascal or Newton per mm square. Okay, so here you can observe here 1 gigapascal. G means capital G means giga Pa means pascal, gigapascal. 10 power 9 giga equal to 10 power 9 pascals, 10 power 9 pascals, or 10 power 3 megapascals, or 10 power 3 Newton per mm square. These are the units for Young's modulus. Okay, so the given data is here. First of all, the size of the bar is given, that is the diameter 25 mm. This is a uniform cross section. That means there is no change in diameter. Okay, the diameter of the bar is same at all points. Okay, so the diameter of the bar AB is same, the diameter of the bar BC also same, the diameter of the CD also same. Okay, so by using diameter 25 mm, first of all you have to find out the cross sectional areas. So the cross sectional area of a bar AB equal to A1, and the cross sectional area of a BC equal to A2, and A3 is the cross sectional area of a section CD. Okay, okay, this is diameter D. Okay, so diameter D equal to 25 mm. Okay, diameter D equal to 25 mm. So 25 mm is the diameter of the this bar. So by using diameter D equal to 25 mm, cross sectional area for bar AB, bar BC, and bar CD equal to A1 equal to A2 equal to A3 equal to pi by 4 D square. Pi by 4 D square is the formula for circular cross sections. So the answer for here, the answer is so the cross section area is equal to 490.887 mm square. Okay, this is the cross section area of each section, and then after here L1, L2, L3 are the original lengths. Okay, L1, L2, L3, 500, 700, 800. These three are original lengths. Okay, and Young's modulus capital E equal to 200 gigapascal. Here the area and the lengths both are in mm. So you have to convert this Young's modulus into mms. Okay, so 1 gigapascal equal to 10 power 3 megapascal. So 10 power 3 megapascal, 1 mega equal to 1 Newton per mm square. So 10 power 3 Newton per mm square is equal to 1 gigapascal. Okay, 1 gigapascal equal to 10 power 3 Newton per mm square. So the Young's modulus value equal to 200 into 10 power 3 Newton per mm square. Here, so all values are in mms. Okay, so the final answer also in mm. That is the total deformation or total elongation also in mm. Okay, now okay, first of all, for solving this problem, first you have to convert this diagram into small diagrams, that is the free body diagrams. Okay, I consider this AB section as section 1. Okay, so here AB, this one is AB, the length L1 equal to 500. I consider 500 mm length as one section. Here the load acting at point A is equal to 60 kilonewtons. So I consider this 60 kilonewtons as load P1. Okay, P1 is the load acting on the bar AB. So For already we know the formula for stress. Already we know the definition about stress. The when you are applying two equal and opposite pull loads on the body, then the stress induced in the body is called tensile stress. So we need two equal and opposite forces to find out the stress. Okay, so to find out the stress or strain, we need two equal and opposite forces. But at point B, the load is 10 kilonewtons, but we need 60 kilonewtons. 60 kilonewtons at B. That's why I am considering two equal and opposite loads like this. Okay, I added two equal and opposite 60 kilonewton loads. Okay, there is no change in elongation because here I added plus and minus value. Okay, right side and left side. If you are considering right side as positive, left side as negative, then both are cancelled. Okay, there is no change in deformation or there is no change in forces. Okay, just I added two equal and opposite forces because I want 60 kilonewtons at end B. Okay, so I need two equal and opposite forces, so that's why I consider this 60 kilonewton because this one is in left side direction. I need right side direction load, so this one is right side load, so I consider this 60 kilonewtons right side load as here. Okay, so this is the free body diagram for section 1. Okay, so I consider this one AB as bar 1 or section 1. Okay, so the loads acting on the bar AB equal 60 kilonewtons. I consider this 60 kilonewtons as load P1. Okay, now then after I consider this last section CD as section 3. Okay, so here you can observe here the load acting at end D equal to 50 kilonewtons. So I consider this as a P3 load because this is a section 3. So the load acting on the section 3 equal to P3. Okay, P3 is the load acting on the section 3. Okay, here also we need two equal and opposite loads at CD bar. Okay, here one load is in right side direction 50 kilonewtons, but another load is 20 kilonewtons, but these two are not equal, so I need equal and opposite forces. That's why now I am adding two equal and opposite 50 kilonewton loads at C point. Okay, now I consider opposite load means here this load is in right side direction, but I need left side 50 kilonewtons load. That's why I consider this load, this left side 50 kilonewtons load as here. Okay, so I consider this load here. So here the load acting on the CD bar is same. Okay, so the load acting on the bar CD equal to 50 kilonewtons. These two are both are in equal and opposite direction. Okay, now you can easily find out the stress induced in the bar CD. Okay, so here the load acting on the bar AB equal to 60 kilonewtons. The load acting on the bar CD equal to P3 50 kilonewtons. Now you have to consider this middle section as section 2. Okay, here already the loads acting on the part B equal to 10 kilonewtons, 60 kilonewtons, 60. Here, this right side 60 kilonewtons already we consider for bar AB. So the remaining two forces are left side 10 kilonewtons and left side 60 kilonewtons. These two are loads acting at B end. Okay, and here also this 50 kilonewtons load already we consider for bar CD. The remaining loads are 20 kilonewtons and 50 kilonewtons at section C. Okay, So you have to consider these two loads at section C. So here this one is in right side direction, this one also in right side direction. So here the load acting on bar C on at NC equal to 20 and 50. So these two loads are the loads acting on the bar 2. Okay, so I consider these two loads, the sum of these two loads as load P2. Okay, P2 equal to 20 plus 50 equals 70, and here the load 10 plus 60 equals 70. So here the condition is is in equilibrium position. That means here you can observe here we need two equal and opposite loads. So here at right side the load acting at NC equal to 50 plus 20 equal to 70. Similarly, the load acting at end B equal to 10 plus 60 equal to 70. So both are same. Okay, and both are in equal and opposite direction. These two loads are in left side direction, these two loads are in right side direction. That means two forces are in equal and opposite direction. So you can easily find out the stress for this middle section. Okay, so these are the loads acting on the bar. Okay, the load acting on the bar AB equal to P1 equals 60, and the load acting on the middle bar, this is the middle bar, the load acting on the middle bar P2 equal to 70, and the load acting on the bar CD equal to P3 equal to 50. So these three loads are the individual loads acting on the bar AB, BC and CD. Okay, by using these three values, you have to find out the stress induced in each bar and strain and deformations. So these are the areas. Here the bar is in uniform cross section. So the area for section 1, section 2, section 3 all are equal. So A1 equal to A2 equal to A3 equal to pi by 4 d square equal to 490.887 mm square. Here d is the diameter of the bar. Okay, now already Young's modulus, already we know the Young's modulus. This one is already given in problem. So Young's modulus equal 200 gigapascal equal 200 into 10 power 3 Newton per mm square. And original length already given in diagram. So L1 is the length of the bar AB, L2 is the length of the bar BC, L3 is the length of the bar CD. Okay, these are the original lengths. Okay, and already we found the loads, individual loads. That is the load acting on the bar. The load acting on the bar AB equal to 60 kilonewtons. It is a tensile load, so positive. Okay, and 1 kilonewton equal to 1000 newtons, so 60,000 newtons. P2 is the load acting on the bar BC, so that is also tensile load, so plus 70 kilonewtons, 70,000. And the load acting on the bars CD equal to P3 equal to 50 kilonewtons equal to 50,000 newtons. Here the load acting on bar AB, BC, CD, these three are tensile loads. So I consider positive sign for tensile loads. Okay, so it is very important the sign positive sign for tensile loads and negative sign for compressed loads. Okay, already we know the formula for stress induced in the bar AB equal to sigma 1 equal to P1 by A1. So P1 is the load acting on the bar 1 by area of the bar 1. So similarly, stress in the bar 2 equal to sigma 2 equal to P2 by A2. Here you have to substitute the values of P1, A1, P2, A2. You will get the values. There is a stresses induced in each bar. This is the formula for stress induced in the bar 3. That is sigma 3 equal to P3 by A3. This is the formula for change in length. Change in length equal to strain into original length. Okay, change in length or deformation equal to strain into L. L is the original length. Here L1, L2, L3 are the original lengths. Okay, the formula for change in length equal to P1 L1 by E1 A1. So here P1 by E1 A1 is the strain. Okay, now these are the formulas for change in lengths. delta L1 is the change in length in bar 1, delta L2 is the change in length in bar 2, delta L3 is the change in length in bar 3. Okay, by using these three values, you have to find out the value of total change in length, or total deformation. By adding these three values, you will get total deformation or total change in length. Okay, so the formula for total change in length or total deformation is equal to delta L is equal to the sum of these three deformations. So P1 L1 by E1 A1 plus P2 L2 by E2 EA2 plus P3 L3 by E3 A3. You have to consider positive sign for tensile loads, negative sign for compressive loads. It is very important. Okay, so you can get answer total deformation or total change in length, that is delta L equal to 1.2121 mm. So this is the total change in length. Here this is a positive value, so the positive means extension or increase in length. Okay, it indicates increase in length or extension. Okay, so the total change in length in compound bar equal to delta L equal to 1.21 mm. So this is the answer for this problem. Now I'm going to explain another problem. Yeah, a steel bar 40 mm diameter is acted upon by forces as shown in figure. Find the total change in length in the bar. Take Young's modulus equal to 105 GPa. Here the problem is same, but the loads acting on the bar, is different. Okay. Here you can observe here same figure already we discussed in previous problem. Okay. Here this one also a uniform cross section. That means same diameter. Okay, the diameter of AB, diameter of BC, diameter of CD, these three are same, so that value diameter equal to 40 mm. Okay, so L1, L2, L3 are the original lengths. L1 is the length of the bar AB, L2 is the length of the bar BC, L3 is the length of the bar CD. L1, L2, L3 original lengths. Okay, these three are in mm. Okay, so loads are in kilonewtons. And lengths are in mm. And here the given data is the given bar is uniform diameter, so 40 mm is the diameter. So the areas are same, that is area of a bar AB equal to area of a bar BC equal to area of a bar CD. So A1 equal to A2 equal to A3 equal to pi by 4 d square. D is the diameter of the bar, that is 40 mm. Okay, so the answer is 1256.64 mm square. Okay, so this is the area of the bar. Now Young's modulus already given in problem, that is Young's modulus equal to 105 gigapascal. 1 gigapascal equal to 10 power 3 Newton per mm square. So 105 into 10 power 3 Newton per mm square is the Young's modulus, and L1, L2, L3, these three are original lengths. Okay, by using these details you have to find out the total change in length, or total deformation. Here you can observe here this is a compressive load. Okay, this is a tensile load. So here you have to consider positive sign for tensile loads, negative sign for compressive loads. It is very important. Okay, I consider same diagram here. Okay, already we discussed the procedure for solving this type of problems. Okay, first you have to split up this compound bar into three sections. That is, I consider AB as section 1, that is bar 1, BC as bar 2, and CD as bar 3. Okay, here I can first of all I consider this bar AB. So this is the bar AB. Here the load acting at the point A equal to 20 kilonewtons. I consider this load as P1 because I consider this section as section 1. So P1 is the load acting on the section 1. Okay, that is 20 kilonewtons. Okay, already we discussed about stress. Okay, we need two equal and opposite forces. Okay, for determining the stress, we need two equal and opposite forces. But at end B, the load is 70 kilonewtons, but we want 20 kilonewtons. Okay, we need 20 kilonewtons at B. So now I am adding two equal and opposite forces like this. So I added 20 kilonewtons in left side and right side. So that means there is no change in deformation, because here this one is acting right side, this one is acting left side. So both are same, equal and opposite. So both are acting at a same point. That means there is no change. There is no change in deformation, or there is no change in stress. Okay. So now I am considering this force 20 kilonewton. I need right side force, because for determining the stresses, we need two equal and opposite forces. So this one is in left side direction, so I need right side direction load. So I consider this right side 20 kilonewtons here. Okay, so now P1 equal 20, P1 equal 20. So these two are equal and opposite directions. So you can easily find out the stress induced in the bar AB. Okay. Now I am considering this section CD as a third section. So first of all, I consider this section. Okay, here the load acting at end D equal to 30 kilonewtons. I consider this load as P3. Here I consider negative sign. Okay, here I consider positive sign. Here these loads are tensile loads. Okay, these two are pull loads. Okay, pull loads are tensile loads, so you have to consider positive sign. But here you can observe here, this is a compressive load. Okay, compressive load means push load. Okay, so you have to consider negative sign for compressive loads. Okay, here P3 is the load acting on the bar CD. Okay, here also I need two equal and opposite push loads. So but at section C there is no load, that is here at section C I have only 20 kilonewtons load, but I need 30 kilonewtons load at C. That's why I am adding two equal and opposite loads. Okay, I need 30 kilonewtons at C. Okay, I need at C. Okay, so that's why I am adding two equal and opposite 30 kilonewtons load. So here also there is no change in deformation, or there is no change in stresses, because I am adding two equal and opposite forces at a common point. Okay, now I need right side 30 kilonewtons load. I need this one. I need this 30 kilonewtons load. Okay, so I am considering this 30 kilonewtons at C, because I need two equal and opposite forces. Okay, now the load acting on bar 3 equal to 30 kilonewtons, but here I consider negative sign for compressive loads. Okay, it is very important, negative sign for compression. Okay, negative sign for compressive loads. Now I am going to considering a middle portion as section 2. I am considering this middle portion as section 2. So here this 20 kilo right side 20 kilometers, I consider here this 30 kilonewtons load considered here. Okay, so the remaining forces are at B. The remaining forces at B are 70, right side 70 kilonewtons and left side 20 kilonewtons load. At section C, the left side 20 kilonewtons load and left side 30 kilonewtons. These two are remaining forces at C point. Now the sum of these two loads and these two loads are the load acting on the bar 2. Okay, so here you have to consider compressive load as a negative sign and positive sign as tensile loads. Okay, that's why at C the total load equal to P2. P2 is the load acting on the bar 2, that is P2 equal to minus 30 minus 20. These two are compressive loads. So that's why I am considering negative sign for compressive loads. So minus 30 and minus 20. So the total load equal to minus 50, as well as at end B the total load equal to here 70 kilonewtons is a compressive load, so minus 70, and this 20 load as a tensile load. So I am considering positive sign for tensile loads. So the total load acting on the bar BC equal to minus 50. Minus 50 means compressive load. Okay, so here P1 is the plus 20, P2 is minus 50, P3 is the minus 30. Okay, so minus means compressive load, plus means tensile load. Okay, already we found the value of area. So this is the area of the bar, this is the Young's modulus. Already these two values are given in problem, and L1, L2, L3 as the original lengths. Okay, and the corresponding loads, the load acting on the bar AB equal to plus 20 kilonewtons. That means tensile load, and P2 is the load acting on the bar BC, that is minus 50 kilonewtons. Minus means compressive load. Okay, this value is minus 50,000 newtons. Okay, negative sign for compressive load. Similarly, P3 equal to minus 30 kilonewtons. So here also this one is also compressive load. So minus 30,000 newtons. Okay, these three are the loads acting on the individual bars. Already we know the formula for stress. Stress induced in the bar 1 equals sigma 1. Sigma 2 is the stress induced in the bar 2. Here P1 is positive, P2 is the negative, and P3 also negative. So here the stresses also positive for tensile stresses and negative for compressive stresses. Okay, and delta L is the change in length. Change in length equals strain into original length. So these three are the individual lengths. Here P1 is the tensile load. So there is an increase in length in bar AB, but P2, P3, these two are compressive loads. So there is compression. There is compression in length. Okay, so compression in length due to compressive loads. So here positive length, here negative length. Okay, positive for tensile, negative for compression. So the total change in length or total deformation delta L equal to P1, the sum of these three deformations, that is P1 L1 by E1 A1 plus P2 L2 by E2 A2 plus P3 L3 by E3 A3. This is the total deformation in the bar. The answer is minus 0.394 mm. Okay, here the negative sign indicates decrease in length, that is compression. Okay, due to loads P1, P2, P3, there is in compression in the bar. Okay, so this is the answer for second problem. Now I am going to explain about another problem. This is a bars of varying cross sections. Okay, the previous two problems are uniform bars, but this is a bars of varying cross sections example. So here you can observe here, this one is a bigger, larger diameter, this one has 30 and 30 smaller diameters. So this example for bars of varying cross sections. Here a steel bar 1.8 meters long. This is the original length of the bar from A to D. The distance between A to D is 1.8 meters. Is acted upon by forces as shown in figure. Find the total elongation. Total elongation or total deformation in the bar. Take Young's modulus equal to 200 gigapascal. Okay, these three are the original lengths. L1, L2, L3 are the original lengths. Here these three are same. Okay, so L1 equal L2 equal L3 equal 600 mm, but areas are different. Okay, here the diameter is 30 mm, here the diameter is 40 mm, here the diameter is 30 mm. So the bar AB and bar CD having same diameter. So A1 and A3, area A1 and area A3 is same, but here the middle section having diameter 40 mm. Okay, that's why this middle section having a different cross section area. The given data is Young's modulus equal to 200 gigapascal. So 1 gigapascal 10 power 3 Newton per mm square. L1, L2, L3 are the original lengths. Here these three are same. L1 equal to L2 equal to L3 equal to 600 mm. And A1 is the area of the bar AB. Here the diameter, I consider this diameter as D1. Okay, so the area of a bar AB equal to pi by 4 D1 square. Here D1 equal to 30 mm, so A1 equal to 706.86 mm square. And here the diameter of the bar BC equal to 40 mm, so the area A2 equal to pi by 4 D2 square. D2 equal to 40 mm, so the area A2 equal to 1256.64 mm square. Similarly, here the diameter is 30 mm. Okay, the diameter of CD bar equal to 30 mm. So I consider this one as D3. D3 equal to 30 mm. So area A3 equal to pi by 4 D3 square. Okay, the area A3 equal to 706.86 mm square. Okay, here A1 and A3 both are having same diameter. So these two are having same areas. Okay. By using these values, you have to find out the total change in length or total deformation. Okay, this is a given diagram. Now first of all you have to draw a free body diagrams. So now I am considering this bar AB as section 1. Okay, here at end A we have 100 kilonewtons load. So I consider this load 100 kilonewtons as P1. P1 is the load acting on the bar AB. Now at end B we have another load that is 50 kilonewtons, but I need two equal and opposite loads. For determining the stresses and strains, we need two equal and opposite loads. But at end B, we have 50 kilonewtons, but I need 100 kilonewtons. That's why I am adding two equal and opposite loads at end B. Okay. So here I am adding 100 kilonewtons right side and left side at a common point. So that's why there is no change in deformation, because I am adding two equal and opposite loads at a common point. So both are cancelled. Okay. Now you have to consider this right side 100 kilonewtons for section AB, because for determining the stresses we need two equal and opposite loads. That's why I am considering this 100 kilonewtons load here. Okay, so this is in left side direction, this one is in right side direction. So you can easily find out the stress induced in the bar AB. Okay, now I am considering this section CD as a third section. Okay, here at end D, the load is 120 kilonewtons. So I consider this 120 kilonewtons as P3 load. Okay. Now here also we need two equal and opposite loads, but at end C we have 70 kilonewtons load, but we need 120 kilonewtons at C. Okay. So that's why I am adding 120 kilonewtons at C. Okay, I am adding two equal and opposite 120 kilonewtons load. Okay, these two loads are acting at a common point. So here also there is no change in deformation, and also there is no change in stresses. Okay, here I need left side 120 kilonewtons load. So I need this one. I need this left side load. So I am considering this load here. Okay, so here you can observe here this section 3 or bar CD having two equal and opposite loads. So now you can easily find out the stress induced in the bar CD. Okay, now you have to consider this middle section as section 2. So here I consider this 100 kilonewtons here. I consider this 120 kilonewtons here. Okay, you have to write down remaining loads for section 2. Okay, the remaining loads at B, at end B equal to right side 50 and left side 100. Okay, left side 100 kilonewtons as tensile load. This one is a tensile load, so you have to consider a positive sign, and this one 50 kilonewtons load as a compressive load, so you have to consider this as a negative sign. Okay, now the remaining loads at end C equal to 120, this 120 kilonewtons load and this 70 kilonewtons load. So here also this one is a tensile load. You have to consider positive sign for 120 kilonewtons, and this one is a compressive load. So you have to consider negative sign for 70 kilonewtons load. So the load, the sum of these two loads as P2. Okay, this is sum of these two loads as P2. So the load acting on the bar BC equal to P2 equal to 120 minus 70. 120 as a tensile load, 70 as a compressive load. That's why I am taking negative sign for compression loads. So the total load acting on the bar at C equal to 50 kilonewtons load. Similarly, the load acting on the bar at end B equal to 100 minus 50. Here 100 is the tensile load and 50 is the compressive load. So I consider negative sign for compression. So P2 equal to 50, P2 equal to 50. So we say it satisfy the condition. So now you can, here you can easily find out the stress induced in the bar BC. Here the load acting on the bar AB equal to tensile load, that is P1 equal to 100. So you have to consider positive sign. Here also the load acting on the in the bar CD also positive sign, because these two are tensile loads. Here also the value P2 also positive sign, that means tensile load. So P1, P2, P3, these three are in positive sign, that means tensile loads. These three are tensile loads. The now here from figure L1, L2, L3 are the original lengths, that these three are equal, that is 600 mm. And already we found the areas A1 equal to A2 equal to A3. These three are the individual areas. A1 is equal to area of the bar AB, A2 is the area of the bar BC, A3 is the area of the bar CD. Okay. Now P1 is the load acting on the bar AB, that is also a tensile load. So positive 100 kilonewtons is the load acting on the bar AB. P2 is the load acting on the bar BC, that is also tensile load. So plus 50 kilonewtons. P3 equal to load acting on the bar CD, that one also positive sign for tensile loads, that is a plus 120 kilonewtons. By using these values, you have to find out stresses induced in each bar. Okay, sigma 1 is the stress induced in the bar 1, that is bar AB. Now sigma 2 is the stress induced in the bar BC. Sigma 3 is the stress induced in the bar CD. Okay. By substituting the values A1, P1, A2, P2, A3, P3 values, you can get stresses, individual stresses induced in the bar. Now, already we know the formula for change in length. Change in length equal to strain in the bar into original length. L1, L2, L3. Here L1, L2, L3 are the original lengths. Okay. So delta L1 is the change in length in bar AB. Delta L2 is the change in length in bar BC. Delta L3 is the change in length in bar CD. Okay. The total change in length or total deformation is obtained by adding these three values, because the total deformation is equal to sum of individual deformations. So delta L equal to delta L1 plus delta L2 plus delta L3. This is the formula for total change in deformation. So by substituting all these values in this equation, you will get the final answer, that is the delta L equal to 1.0531 is the answer of this problem. Here the value delta L is in positive sign. That's why, that means there is an increase in length in the bar due to the loads P1 and P2 and P3. Okay. So this is the answer for this problem. Okay friends. These three problems are very important in exam point of view. Okay. In next class, I will explain some example problems on bars, on composite bars or compound bars. Okay. Those problems are also very important in exam point of view. Okay, friends. Okay, friends. Thank you.